This next section, we're going to be talking about integration by substitution. Integration by substitution is essentially the chain rule for integrals. So, since integrals are the inverse, basically, of a derivative, we'd like to look at derivatives to start with. So we're going to look at the chain rule as it relates to derivatives. Here we have an expression that f of x is the quantity 2x squared plus 7 all raised to the 10th power. And if we take a derivative of that, we notice that we have an inside function and an outside function. The inside function is the 2x squared plus 7. That's this function inside the parentheses. The outside function is going to be that thing raised to the 10th. So to take the derivative, we multiply by the exponent, 10, subtract 1 from the exponent, leave what's in the parentheses alone, 2x squared plus 7, and then we multiply by the derivative of what's in the parentheses. And so this 4x, this is the chain rule. And then in the next step, we just simplified it a little bit. We took the 10 times the 4x, and we came up with 40x. So that's the chain rule. Now, we can work that backwards if we want. So if we took an integral, we would know what the answer was. If you take the integral of 2x squared plus 7 all raised to the 9th times 40x dx, well, you know what the integral is because you took the derivative of 2x squared plus 7 to the 10th to get that other expression. And then we do get this plus c on here because when you're integrating, you don't actually know what the original function was. So you have to add the plus c so that you can account for any constant that might have been in there. Now, the hard part is recognizing this integral. When we had something like x to the 4th or x to the 10th, it was very easy because it was just x raised to a power. When you have the chain rule, it's not so easy, and you have to do something known as a u-substitution. So what we're going to do is we're going to rewrite our expression so that it only has one variable instead of a complicated polynomial in that parentheses. So we're going to take that entire 2x squared plus 7 and we're going to replace it with one single letter that we call u. Now, this next example is slightly different than the first one because I have only 4x instead of 40x. So the answer is not going to be exactly the same because what I'm integrating is a tiny bit different. So the very first thing we do here is we take and we say, well, I'm going to let u be this expression in the parentheses. And the reason I do that is because if we had an integral that was u raised to the 9th du, well, I could integrate that. That would be u to the 10th over 10 plus c. And that would be easy to integrate. So that's what I'd like to have happen. I want to set this up so that I have exactly u to the 9th du. The trick there is that you have to have du. And du here is the derivative of u. Derivative of u. So that means whatever's in the parentheses, you have to have the derivative of that right beside there so that you can integrate. So the first thing we do is we write down u here. We say u is equal to 2x squared plus 7. Then once you've selected u, you have to know what du is. And so du is the derivative of u, and that's just 4x. Now, it's really du dx, but I want my du by itself on the left, so I take the dx and I move it over here to the right-hand side. So what that tells me is that du is 4x dx. And now what I can do is I can rewrite that integral. And I'm going to do that on a new page here. So what we did, we started off with the integral of 2x squared plus 7 to the 9th times 4x dx. And we said, well, we're going to let u equal 2x squared plus 7. Du, the derivative of u, is 4x dx. And now I can substitute. This 4x dx, that's du. And this 2x squared plus 7, that's u. And so I get exactly what I want. I get u to the 9th du. I substitute du in there, and u inside the parentheses. And we know what that integral is. That's u to the 10th over 10 plus c. Now, my original problem was in terms of x, not in terms of u. So you have to rewrite this in terms of x. And so u was 2x squared plus 7, all raised to the 10th now, divided by 10 plus c. And that's using the chain rule in reverse. And if you want to check your answer, you can simply take the derivative. So if you start with this thing, if you say, well, okay, what if f of x is exactly that expression, 2x squared plus 7 to the 10th over 10 plus c, then f prime of x, see, I multiply by the exponent, I leave what's in the parentheses alone, 2x squared plus 7, subtract 1 from the exponent, I still have this 10 in the denominator, and the derivative of the constant is 0. And sure enough, the 10's cancel, and you're right back to where you started. Oh, sorry, times the derivative of what's in the parentheses, 4x. And you're right back to where you started. Don't forget the chain. So anytime you take an integral, whether you use the u-substitution or not, you can always check your answer by taking a derivative and getting back to where you started. This next example is very similar, except that now I have some variables in the denominator. So, the very first thing we need to do is we need to write this so that I have that expression in the denominator, which is raised to the 3rd power. I'm going to move that to the numerator by changing that exponent to a -3. So what we get here is we get the integral of 2x squared plus 3 to the -3 power times 4x dx. And now I'm going to do the same thing I did before. I'd like this to be an expression u to the -3 times the derivative of u. So I'm going to say, well, let's let u equal 2x squared plus 3. Then the derivative of u is 4x dx. I have exactly that, so I'm in good shape here. Let's separate this. And so we have the integral of u to the minus 3 du. Because I take u and I put it in there, and I take du and I replace that 4x dx. And if you integrate that, you add 1 to the exponent, so you get u to the minus 2, and you divide by the exponent. And then, of course, you want it back in terms of x, so you get 2x squared plus 3 raised to the minus 2 power divided by negative 2 plus c. So sometimes with these problems, you have to do a little bit of algebra first before you can actually do some calculus to them. We had that same situation very often when we were working with derivatives. Here's another one that's fairly similar. This one's going to have a little bit of a change because I don't have my exact du available. So for example, here, this expression in the parentheses, I'm going to let that be u, x cubed minus 1. Because I would like this to be u to the 9th times the derivative of u. So we're going to say, okay, so u is going to be x cubed minus 1. The derivative of u, or du, is 3x squared dx. Now, the problem is that my du is 3x squared dx, but I don't have 3x squared dx. I only have x squared dx. Now at this point there are many different algebraic ways to solve the problem, and I'm going to show you 2 of them. Here we have x squared dx in the original integral. I have the integral of x cubed minus 1 to the 9th times x squared dx. And what I want to do is I want to convert everything into u and du. So what I do is I solve my du equation for x squared dx, because that's exactly what's in my original integral. So if you solve it for x squared dx, that's equal to du over 3. And now what we can do is now we can do our substitution. We get u to the 9th for x cubed minus 1 raised to the 9th. And x squared dx, I know what that is. That's du over 3. Now, still not exactly right because I still have that over 3 there inside the integral. But I have a rule, and that rule says that if I have a constant, I can move it outside the integral. And that 3 in the denominator is a constant. It's essentially 1/3. And so I'm going to move that out in front. And I get 1/3 the integral of u to the 9th du, which we can integrate. That's 1/3 u to the 10th over 10 plus c. Again, we don't want it in terms of u. We would like it in terms of x. And I'm also going to multiply the 3 times the 10 to get 1 over 30 times x cubed minus 1 to the 10th plus c. So that's one way to solve these problems. You solve your du expression for what you have in your integral. In this case, I had x squared dx, so I solved for x squared dx. Another way to do this problem is the following. If you start off here with x cubed minus 1 to the 9th, what I'm going to do is I'm going to leave a little space here between x cubed minus 1 to the 9th and the x squared dx. And I leave that space because I'm going to try to fix the problem using that space the following way. We say u is still x cubed minus 1, and du is 3x squared dx. And so what we do is we look up here in the problem, and we notice that we have x squared dx, and in du I have x squared dx, but I still need a 3. So what I'm going to do is I'm going to come up to the original problem, and I'm just going to stick a 3 in there. 3 times x squared dx. Now I have exactly u. If you multiply by 3 on the inside, you've changed the value of the problem. So you need to fix that by multiplying by 1/3 the reciprocal on the outside. So multiply by 3 inside and 1/3 outside, and that's the same as multiplying by 1. And I haven't changed the value of the problem. Now I can do my change of variables, and I get u to the 9th du, and we know how that works now. It's u to the 10th over 10 plus c. Convert it all back over to x's, and you get x cubed minus 1 to the 10th plus c. Some people prefer the first method because it makes the substitution a little bit more straightforward. This method does require you to think a little bit more. However, it probably saves you a step. This is the method I will use from now on. I will multiply inside the integral by a constant, and then multiply outside by the reciprocal of that constant. Now this technique only works with constants, because you can move constants inside and outside the integral. You cannot do this with a variable. If you are missing an x, you cannot multiply by x. You can only multiply by constants. So here's another example, which I'm going to rewrite. I'm going to write it like this: e to the 2 minus x. And then what I'm going to do is I'm going to leave myself a space so that I can fix my du. So I'm going to make a note here, leave a space, leave a space right in front of your dx term so that you can multiply by the constant that you need to multiply. So in this case, what I'd like is the integral of e to the u du, because that integral is simply going to be e to the u plus c. So if I want e to the u, well, then whatever's in the exponent is going to be my u. And in this case, that's 2 minus x. Then the derivative of u is -1 dx So I look at my original problem, and I notice that I've got e to the 2 minus x. That's fine. But then I do not have negative 1 times dx. I just have dx. So what am I going to do? I'm going to multiply by negative 1 on the inside. But again, I don't want to change the value of the problem, so I multiply by a negative 1 on the outside. Now, we can rewrite everything in terms of u. I have negative integral e to the u du. And I know that answer. That's e to the u plus c with a negative sign, negative e to the u plus c. That negative just comes down. And I don't want it in terms of u, I want it in terms of x, so I get negative e to the 2 minus x plus c. So this technique of multiplying by a constant also applies to a negative, because a negative is really just multiplication by negative 1. Sometimes we have to use two different u's. In this case, we have two different integrals. We've got the integral of e to the 2x, and we have the integral of e to the minus 3x. So what I'm going to do is I'm going to rewrite this so that I can do the two integrals separately. So I'm going to pick two different u's. So the first thing I'm going to do is I'm going to rewrite this as the integral of e to the 2x dx. And again, I'm going to leave a space in here so that I can fix my integral, plus the integral of e to the minus 3x dx. And again, I'm going to leave a space in here so that I can fix my integral. So, I'm going to pick two different u's. For the first expression, I have e to the 2x, so u1 is going to be 2x. The derivative of u1 is going to be 2 dx. u2, that's going to be my second u, is going to be negative 3x. The derivative of u2 is going to be negative 3 dx. So for the first integral, I go up and look. I want 2 dx, but I only have 1 dx. Let me put it here in red. So I put a 2 inside, and I fix it with a 1/2 outside. For the next expression, I want the negative 3 dx, but I don't have that. All I have is dx. So I multiply by negative 3 inside, and I have to fix it with a negative 1/3 outside. You have to multiply by the reciprocal, and don't forget the negative sign. Now I can rewrite this in terms of u. 1/2 e to the u du integral. Whoops. And then minus 1/3 integral e to the u du. Oh, that's u1 and u2. So if you integrate the first one, you get 1/2 e to the u1. And if you integrate the second one, you get negative 1/3 e to the u2. And I'm going to put one single plus c on both of those integrals. We need to convert it all back into x's, so we get e to the 1/2 e to the 2x minus 1/3 e to the negative 3x plus c. So for some of these, you have to do 2 substitutions, not just 1. This next example is always the hardest one, because the temptation here is to write it as 3x plus 7 raised to the minus 1 power. But anytime you have something raised to the minus 1 power, it's actually going to integrate as the natural log. And so what we want here is we want the integral of 1 over u du. Because if I integrate 1 over u du, I get the natural log of the absolute value of u plus c. Since that's what we would like, that's what we're going to make happen here. I'm going to let 3x plus 7 be u. Du is 3 dx. I don't have the 3, so I'm going to put it in here, and I'm going to fix it with a 1/3 out front. So what do we get here? We get 1/3 integral of 1 over u du, which is exactly what we wanted. So we get 1/3 natural log of the absolute value of u plus c. And we don't want it in terms of u, so we convert it back into natural log of 3x plus 7. And you have the solution. If you have anything more complicated than simply an x or a single variable, you almost invariably have to use a u-substitution. Now, there are some exceptions to that rule. Sometimes you can do a little bit of algebra and get this to work out nicely. Here, for example, if we take the integral of 1 over 3x dx, we could do a u-substitution. U is equal to 3x, du is equal to 3dx, and so on. But instead of doing that, what I'm going to notice is that 3 in the denominator, that's really a 1/3. This is the same as the integral of 1/3 times 1 over x dx. And I can take that integral, I can take that 1/3, and I can move it out in front of the integral, and you get 1/3 1 over x dx. You know what that is. That's the integral of 1 over x is natural log of x. So sometimes it may appear that you need to do a u-substitution, but if you do a little bit of algebra and you factor out the constants, you can sometimes get away with not doing a u-substitution or possibly doing a simpler u-substitution. So if you can, factor out any constants. That concludes the lesson on integration by substitution.